Okay, this next section, continuing our work in Chapter 37, is on 37.3. where we discuss Lorentz contraction and time dilation. The first of these is Lorentz contraction. Using those postulates, Einstein was able to show that if you have an object of a given length, normally called L naught, and that object is moving with a velocity v past you, you will see it with a different length, L, like if you photograph it. So you take a camera here, and you photograph it against a background, and you say, well, I know that that is a meter stick. How long does it appear to me as I photograph it? The answer is the length that you will observe by the camera. That's your length. Will be equal to the length that it normally is when you are at rest with respect to it, times the square root of 1 minus v squared over c squared. This equation right here, which will be used on the exams, is called the Lorentz contraction. And it has been fully confirmed in experiments to date that Einstein was correct, that we do have this Lorentz contraction. Let's examine it and see what it implies. Well, if I look at this equation, you'd say, well, you know, this says things get shorter and shorter, because here I have 1 minus a velocity squared over c squared. So if this is some number below the speed of light, then I'm going to subtract it from 1, get a number smaller than 1, and so L is going to be short. So we always see objects as compressing, getting shorter. One way is if you went fast enough, here you are, and you have a stomach that is too large and you would like to get rid of it and lower your waistline. By going fast enough, you will get thinner and thinner through here until finally, let's see what happens at the two extremes. Well, if you have no velocity, then v over c is 0, square root of 1 is 1, and L is equal to L naught when velocity is equal to 0. But if the velocity were to get to c, something that's impossible, we'll see later, then we would have v over c, which is c over c, which is 1, 1 squared is 1, 1 minus 1 is 0, and we'd get L is equal to 0. So what happens is as you go faster and faster, you originally see the object at its regular length, but as you get close to the speed of light, it shrinks down to 0, and it has no thickness whatsoever. Well, when do you begin to really notice this? I mean, do you see this in cars going down the road? Absolutely not. Let's look at this when you get to something like 1/10 of the speed of light. At the 1/10 of the speed of light, this v here becomes 0.1 c. Now watch this. This is v is equal to c. Let's look at v is equal to 1/10 of c and see what happens then. At 1/10 c, we get L is equal to L naught, square root of 1 minus, that's 1/10 c over c, so that gives us 1/10 squared, which is 1/100. Now this is the same as L naught times the square root. 1/100 would give us 0.99. The square root of 0.99 is very small. Let me get out my calculator and we'll see what that is. And so we take our calculator and we take 0.99 and go over here and take its square root, and we get 0.995. Well, this is within 5 parts in 1,000 is the same length. So this is very minuscule. That's a very small change. So something that is very long at a tenth of the speed of light only has a change of 0.5% shorter. In order to do that, I have to go how fast? Well, light goes, you recall, at c is equal to 3 times 10 to the 8th meters per second. But let's look at it more realistically. It goes 186,000 miles every second. So the effect that we just barely notice as a 0.5%, 0.5% effect, only happens when our velocity is equal to 1/10 of this, 18,600 miles per second. Now you understand why we do not see these relativistic effects. These relativistic effects only begin to occur at about 18,000 miles a second, faster than anyone has ever observed. That's why we do not see them with our automobiles, our bicycles, or when we're jogging. Nobody jogs at this speed. So in general, we can use this as a kind of an estimate of where relativity begins to take place. It begins to take place when we're moving at least a tenth of the speed of light, or even faster than that, because here the effect is very, very small. This is called Lorentz contraction. Next, let's look at time dilation. Whereas lengths contract, time dilates. You know what it means when your eyes dilate. They get larger. So the time dilation means that time is actually getting longer. And if you have a clock, and this clock is moving by you, and we have an alarm every so often, and that period would be, say, t, not on the clock. If you're sitting next to it, you've set it, the person who's sitting next to this clock sets it to chime, say every hour or something like that. Then as it moves by you at a velocity v, you find that the time, delta t, that you observe is equal to delta t naught divided by the square root of 1 minus v squared over c squared. And likewise, using the same square root here, 0.995, you can see that you're dividing by a fraction, therefore this time is longer. In fact, if the velocity is equal to c, you get 1 over 1 squared. 1 minus that 1 is 0, and you're dividing by 0, so this approaches, we can say that t, delta t, is equal to infinity at v is equal to c. And delta t is equal to delta t naught at v is equal to 0. And in between, again, the square root only makes itself shown as being noticeable. In other words, relativistic effects only are noticeable at about a tenth of c. So therefore, only when we get to about a velocity of c over 10, 1/10 of c, do we begin to see relativistic effects. And here, the delta t would equal to our delta t naught divided by 0.995. You can see that that's very, very small there. These are the two dominant effects: Lorentz contraction here, time dilation here. Time spreads out. So something that moves by you very fast lives longer. As it's going almost the speed of light, your friend, your identical twin, would live for thousands or hundreds of thousands of years relative to you. And he would look at you, but you would look at him in the same way, because each sees the other one moving relatively, and each thinks the other one is going to live longer. Something that we really have to think about.